the maximum flow problem. There is a certain type of a problem that's called the maximum flow problem, in which we try to decide the maximum amount of flow that can go through an entire network. Okay, and in those problems, usually the arcs will have upper bound and lower bound. Okay, for example, if you think about like a transportation network, certain road, there is a limit of cars that can go through, right? Depending on whether it's a 1 lane or 2 lane. If you think about like pipes that transport, say, gas or oil, depending on the diameter of the pipes, a certain amount of the the oil and the gas can go through. So it's not realistic to have no limit on those pipes. But we can determine, okay, what's the maximum flow it can go through. And so let's look at this problem. If you can turn to the problem statement of 5.6 and read the problem statement first. And do this very quickly, and we'll think about how to formulate this problem. Okay, just by looking at it, it's a quite different problem from the ones that we just talked about, right? What we're trying to determine is, okay, with this limits, those values on each arc represent the maximum amount of oil that can go through within that per hour, measured in thousands of barrels per hour. Okay, and we're trying to see, okay, say, okay, if we just send oils to this node 1, okay, within an hour, how much of them can go through this entire network and come out from here? If we think in this way, does it make it easier? Okay, so how much we can send to this node 1, and so they can go through this entire network, whether it go this way or this way or this way or this way. It can go through and go out of this node 6 and go out. Okay, so that's how we how we view that's the maximum amount of oil that can go through this entire network. Some students try to just calculate, okay, add up all those limiting numbers together and say, okay, that's the maximum value. That's not right. Okay, for this problem, you can do a simple analysis. For example, okay, so 6 maximum can go out, and this 6, say here is a 3, and this is a 2, and so together, so this value here and this value together, that's a 5 in total that can go through 6. Oh, sorry, can go to this node 4. Even though 4 to 6, the limiting number is 6, but only maximum. At most, only 5 units can go to this 4. So this 6 is not really useful. So it's a 5 there. That's kind of like a heuristic, which is you solve problem by hand. Okay, I ask you guys to read the textbook in chapter 3. One of the transportation problems, it talk about heuristic. This is one heuristic. So you just based on rule of thumb and do some calculation, and then you find out, okay, what's the possible answer for this question. So in this one, because the network is pretty simple, by some hand calculation, you should be able to find the right answer. However, when the network gets really complex, using heuristic is really difficult, and you may not find the right solution. Okay, so using a structured way to formulate this problem, it's the preferred way to do it. Okay, then based on what I just said, let's think in this way. We're trying to see, okay, let's send out a lot of oil to this node and see how much can come out from this node 6. So why don't we just calculate this flow here. And let's connect these two together. Okay, so we're going to connect this node 6 to node 1. And what one saying is that let's just assume all the oils that get sent out to this node 1 went through this entire network and come out from node 6, and they are all stored in this imaginary pipe that has no upper limit. And as long as we find out what's the maximum value that this flow can be, while having 0, 0, 0, 0, 0 demand here in all those nodes, then we find out what's the maximum that we can send through this network. Okay, I'll say that again. Rethink. Okay, so what we're trying to do is we connect this node 6 to node 1, and we're saying for all the oils that we sent to this node 1, we just assume they went through this network already and come out and get all stocked in this imaginary pipe that has no upper limit. Okay, as long as we maximize this x61 while keeping constraints that make sure no oil got left in those nodes and arcs. Okay, which means set all the demand here at 0 for all of those nodes. Then we can find out what's the maximum that's oil that can go through this network. Think about it. See if it makes sense. So what we're saying will be, okay, for node 1, we have just a 0. So the x61, which is the inflow to node 1, subtract x12, subtract x13, will be 0. Okay, and for all the other nodes, it's the same. It's all inflow minus outflow. Okay, and then for node 6, we're saying x46 plus x56 equals to be, we just do subtract x61. This also equals to 0. By using all the constraints, set all the nodes for inflow outflow equals to be 1. We're saying we don't need any of oil left at any of those nodes. We're going to send all of them out to this imaginary pipe. And let's just maximize this value here. And of course, we need to add those constraints. Okay, for example, here, x12 need to be less than equal to 6. Okay, and x13 need to be less than equal to 4. x24 need to be less than equal to 3. x25 need to be less than equal to 2. So all those limits on each of the arc we need to set. Okay, then besides those constraints, we'll just have 0 demand at all the points, at all the nodes, and we maximize this flow here. Because this is imaginary flow, it has no limit on it. We just maximize that value. Okay. Yes?
Why are you using equal for equations?
What's that?
Why are you using equal for equations?
For those zeros, why do we use equals? Because the purpose is that we want them to be the inflow just equals to the outflows. So that's thinking this way.
How much oil that you're getting through node 1, you want the same amount to go through node 2?
Right, right. So if you consider this one, this is equal to x61 equals to be x12 plus x13. So for all those nodes, what we are saying that the inflow need to be equal to the outflow. So whatever goes in need to come out. So no oil left there. And then all the oil that goes will go to this pipe here. Does that make sense? If we use greater than equal to, is that possible that some oil will be left there? We want to maximize x61. What do you think? If we use greater than equal to,
x61 greater equal to x12 plus x13.
right, if that's what we are saying, then at this point we can, so the inflow x46 plus x56. So that's for node 6. If we say greater than equal to, that does not make much sense, right? So what goes in need to be greater than equal to what comes out. Yeah, so probably does not make sense.
Before defining the sign of the constraint, we were checking the supply and demand.
Okay.
Now we
Okay, so what's the supply in this case? Do we know? We don't know what's the total supply, right? And we don't know what's the total demand, right? So in this case, we're not really following that rule. What we're saying is this way. Still, the constraint is still in the same format, but what we are saying is that we want the inflows equals to be the outflows. We want the demand, actually we're just saying we want the demand at each point, at each node being 0, representing we don't want any oil to be left at each of those points. Okay, and then for this starting node and ending node, we're just saying, okay, what goes out equals to be the value that we're trying to maximize. And that value goes back to 1. So we kind of like connect this entire network into a circulation. But we know that there is no oil at all at each of those nodes and arcs. They are all stored in this node here. And sorry, they are all stored in this arc here, this flow here. And we try to maximize that value based on, and because we try to maximize because of those constraints that each of those arcs here has their limitation, the upper bound. So we won't be able to maximize this to infinity. So there will be a value that we can find out. Okay. Okay, does that make sense now? There are other ways to formulate this problem. What do you guys think? Mm. You are thinking like convert this to the shortest path problem? Probably not, because in this case we really don't have a supply, and we really don't know what the supply and demand is. Like in the shortest path problem, we can assume it's one supply and one demand because we're just thinking transport this one car through this network. And here what we're trying to do is we're trying to know what's the maximum amount we can send, what's the maximum supply we can send, and what's the maximum demand that this node 6 can receive. So there is really no supply or demand that we can put. Does that make sense?
No, because I think like in the other examples, like with the shortest path, or so you're saying it's a maximization problem rather than a minimization problem? Is that the
Minimization problem. Shortest paths, they are all minimization. You minimize the total travel time, right?
Right.
Or the total cost. Yeah, this one want to maximize the supply. No, that's not the basic difference. The basic difference is that here we don't know what the supply amount is. And that's the thing that we're trying to maximize. In all the shortest path problem, like the equipment replacement problem, we just talk about, we can assume that's one supply because we don't want to maximize it. We can assume it's one supply, and our objective is to minimize the total cost to go through that network. Either the total travel time or the total cost. We minimize that part. But in this way, we don't know what the supply is, and we cannot assume it because that's the thing we're trying to find out. We're trying to find out what's the maximum supply that we can carry on this network, or say what's the maximum demand that this node 6 can receive. Okay.
So could we have just said that maximizing x 4, 6, and 4, 5 plus 4, 5?
Okay.
Instead of putting that feedback into
Okay. Yeah.
We've done that as well.
Yes. So that the other way to formulate would be maximize x 4, 6 plus x 5, 6. Okay, so besides this constraint, that's another thing you can do. And instead, then you will have to write the constraint differently. So the constraint, so you won't have this imaginary pipe, right? So we have x4. So what's the demand here then? How do you write the constraint for node 4, node 6? Do you guys get what Caleb suggested? So instead of maximize x61, the other way is to maximize 4,6 plus 5,6, which is this arc and this arc, because these are the final two inflows that goes to this ending node. But how do you write the constraint for node 6? Or do you write the constraint for 6?
The right is constraint for each of them individually. Say x56 has to be less than 5 or 4, and then x46 has to be less than 6.
Okay, but what about the inflow-outflow constraint? Because there is no demand here. And that's the thing that we're trying to maximize. Okay, you know what? I'll leave this for you guys to think. What he suggested is correct. So the objective function can be changed to this way. But I need you to figure out what the constraint should be in this case. Okay, with this objective function, I already told you what are the constraints. So for all the nodes, from node 1 to node 6, you need to write the inflow minus outflow equals to be 0. And for all the cases, we do know what the inflows outflow. Especially for node 1 and node 6, we have this imaginary. So for node 6, you have outflow being x61. And for node 1, you have inflow, which is 61. Okay. Okay, so that's something I'll need you guys to think about. So that's for this problem. I'll just summarize the model that we have. Maximize this imaginary flow, x61. For all the nodes from 1 to 6, you have inflow minus outflow equals to 0. And add those side constraints. So these are the side constraints that we talk about. At the beginning, we said one benefit of the balance of flow rule is that if you have constraints that follow the balance flow rule, for example, this one, balance of flow rule. So those constraints in this format, inflow minus outflow equals to less than equal to greater than equal to demand or supply is the constraint that follow this way. Okay, and if you only have if your other constraints are only side constraints, that's upper lower limit, a simple upper limit, a simple lower or upper limit for your decision variables like these ones. And if your right hand side are all integers, so these are integers, then for sure you will get integer solutions. Okay, for example, in this problem, you don't need to add the integer constraint and you will get integer solutions. Okay, and however, if you add other constraints, say x12 plus x 23, which are not in this case, for example, so the flows to node 1 and 2, 1, 2, 2, 4. Okay, so I just put in this way. Suppose, okay, let me go back, erase this. Suppose there is a constraint saying that, okay, the inflow to node 1 and the inflow to node 2 altogether cannot exceed a certain value. So if you add, say, okay, the inflow to node 2, so would be 1 to 2. And the inflow to node 3 should not exceed a certain value. Say if you have this constraint. Okay, if you have a constraint like this, you're saying, okay, someone say, okay, in total, the inflows to node 2 and the inflow to node 3 should not exceed a unit of 10. If we have a constraint like this is not a balance of flow rule constraint because it's not inflow outflow for a certain node less than equal to a demand. Then it's not guaranteed that you will get integer solution. Okay, if you have to have integer solution, then you need to add that integer constraint. Say, okay, all the xij's being integers. Okay, so that's one thing we emphasize why we prefer to formulate those constraints following this balanced flow rule. Okay, and we're going to implement one problem at the end. Okay, so that's what I'm saying here. This integer values will not hold true if side constraints, just like the one that I talked about, are added. That's not obeying this balanced flow rule. Okay, so because of and we know that I kind of mentioned what's the benefit of not adding integer constraints. First, integer problems solve slowly. Second, more importantly, you won't get sensitivity analysis report if you add integer constraints. Okay, and we spent one week talking about how sensitivity analysis can be useful in revealing some business information. Okay, so that's why it's not preferred to do that.